In this video, we're going to look at estimating sums of alternating series. If a series summation n equals 1 to infinity an, or summation n equals 1 to infinity negative 1 to the n times an converges to a finite sum s, then the remainder is Rn is equal to s minus Sn, where Sn is the partial sum of the first n terms. Absolute value of Rn is equal to absolute value of s minus Sn. This is the absolute error in approximating the sum of the series. Now, S is a sum of the entire series n equals 1 to infinity minus 1 to the n times an. Sn is a sum of the first n term. It's the nth partial sum of the series. So Sn is equal to summation k equals 1 to n, negative 1 to the k times ak. And for a converging alternating series, summation n equals 1 to infinity, negative 1 to the n times an, the size of the error, absolute value of Rn, is equal to absolute value of s minus Sn is less than an plus 1, which is the first omitted term of the series. So to make it simple to understand, if you add the first 5 terms of a converging alternating series, the error is less than the sixth term. If you add the first 10 terms of the alternating series, the error is less than the absolute value of the 11th term. So if you add the first n terms of a alternating series, the error of approximating the sum is less than the n plus 1th term. Of course, the absolute value of the n plus 1th term. All right, so now let's look at the formal definition of the alternating series remainder theorem. If s is equal to n equals 1 to infinity, negative 1 to the n plus 1 times an is a sum of an alternating series that satisfies these two conditions. An plus 1 is less than an, that means the terms are decreasing in magnitude, and limit as n approaches infinity of the general term an is equal to 0, then the remainder term Rn is equal to absolute value of s minus Sn is less than the n plus 1th term. If you add the first n terms, the error of the approximation is less than the n plus 1th term. Now, we're checking the two conditions of convergence because the only way that we can apply this alternating series remainder theorem is if the alternating series converges in the first place. That's why we have to check those conditions first. So let's look at an example. How many terms of the series summation n equals 1 to infinity, negative 1 to the n plus 1 times 1 over n squared have to be added up so that the error is less than 10 to the minus 6? Our strategy will be, number 1, show that the given series converges. Number 2, apply the alternating series remainder theorem to find the number of terms that we have to add up so that the error is less than 10 to the minus 6. All right, so we have summation n equals 1 to infinity, negative 1 to the n plus 1 times 1 over n squared. We're going to prove that this is a convergent alternating series. Convergent alternating series. Now, we need to prove there is convergence, so let's check the two conditions for convergence of an alternating series. Number 1, we have to show that the terms are decreasing in magnitude. An plus 1 is less than an. The n plus 1th term is simply 1 divided by n plus 1 squared. And we have to show that this is less than 1 over n squared. Well, this is very clear because we're making the denominator larger, and hence the ratio becomes smaller. Number 2, the limit as n approaches infinity of an has to be equal to 0. So take the limit of the nth term, limit n approaches infinity of 1 over n squared, 1 divided by a very large number because n is going to infinity, the ratio approaches 0. So both conditions of convergence of the alternating series are satisfied. So now let's express the given series as a sum of the first n terms plus the remainder. So we have summation. I'm going to change the n to k to make it easier to form the nth partial sum. So k equals 1 to infinity minus 1 to the power of k plus 1 times 1 over k squared. This is equal to 1 minus 1 quarter plus 1 over 9 minus 1 over 16. Now let's put the nth term in and the nth term of this series is negative 1 to the n plus 1 divided by n squared. And now let's put the n plus 1th term, which is negative 1 to the power of n plus 2 divided by n plus 1 squared. Now, Sn is the sum of the first n term. This is the nth partial sum Sn. Now, this term is the remainder term. So the absolute value of Rn is equal to absolute value of S minus Sn. This is actually the error term. So the error of our approximation is going to be less than this term. So the error is less than the absolute value of this term. So less than this term. All right. So by the alternating series remainder theorem, we have absolute value of S minus Sn is less than or equal to absolute value of the first omitted term, which is an plus 1. An plus 1, the n plus 1th term of this alternating series is going to be negative 1 to the power of n plus 2 divided by n plus 1 squared. Absolute value gets rid of the negative sign, so we get 1 divided by n plus 1 squared. Now, we know that the error has to be less than 10 to the minus 6, so absolute value of S minus Sn is less than or equal to an plus 1, the n plus 1 term, which is equal to 1 over n plus 1 squared. And this should be less than 0.1235 zeros and a 1, because we need 5 decimal place accuracy, so we need 5 zeros here and a 1. All right, an plus 1 is equal to 1 divided by n plus 1 squared. Let's make this less than 10 to the minus 6. And now flip both sides, we get n plus 1 squared is larger than, and the minus 6 becomes plus 6, because 1 divided by 10 to the minus 6 is equal to 10 to the plus 6. So 10 to the 6, we have to solve for n. Square root both sides, so we get root of n plus 1 squared is larger than root of 10 to the 6. And we get absolute value of n plus 1 is larger than root of 10 to the 6 is going to give us 10 cubed. And since n plus 1 is a positive number, we don't need the absolute value, so we can write absolute value of n plus 1 is the same as n plus 1, larger than 10 cubed, which is just 1,000. Solve for n, subtract 1 from both sides, we get n larger than 999. So let's round up, and we get n equals 1,000, because we need to, n has to be an integer bigger than 999, so we'll take n equals 1,000. That means we need to sum up the first 1,000 terms so that the error is less than the 1,000 first term, which is less than 0.00050, and so we need to add the first 1,000 terms. So we need to add the first 1,000 terms of this series to approximate the sum of this series with error less than 10 to the minus 6. So let's summarize. We have S1000, the sum of the first 1,000 terms of this series. Summation n equals 1 to 1,000, negative 1 to the power of n plus 1, times 1 over n squared. This is equal to 1 minus 1/4 plus 1 over 9 minus 1 over 16, all the way up to the 1,000th term, plus negative 1 to the power of 1,001 divided by 1,000 all squared. All right, so if we add up the first 1,000 terms, the error is less than the 1,000 first term, which happens to be less than 10 to the minus 6. So absolute value of S minus S1000 is less than 10 to the minus 6. It's very important that we realize what these represent. S represents the sum of the entire infinite series, the entire infinite alternating series. S1000 is the sum of the first 1,000 terms. We're approximating the sum of the entire infinite series with the first 1,000 terms, with the sum of the first 1,000 terms. So we like to know what is the error of our summation, or of error of our approximation, the error is less than 10 to the minus 6. So if we add up the first 1,000 terms to approximate the entire sum of this alternating series, the error is less than 10 to the minus 6. All right, thanks.